You gave me first billing? My goodness, I can't believe that. What the hell's going on here?
You're my instructor. You're my
Oh,
mentor.
God.
So
Today is National Mentoring Day. Is it something like that? So,
fantastic.
so it works out just fine.
That's
So
a good one.
appropriate.
Hmm. So
I saw Lisa commented that we were two of her mentors. So
okay, well,
yeah,
good.
yeah.
Looks like YouTube is live.
Yeah,
And
I
we
got nervous. I got nervous and I pulled the trigger early.
we have viewers on YouTube.
Great.
That's too funny. Oh my goodness. Hmm. Are you going to ASTM, Rich?
I think
Uh,
virtually.
Virtually? Same here,
Yeah,
probably.
right. Yeah.
Yeah.
I know that is one event that we really get a lot more out of being there in person. But
Yeah.
with that last minute change, we're just going to, I think, do it that way this time around and hope for spring.
Yeah. Same here.
Yep. Okay, I think we can get started, Richard, if you want to kind of do an introduction.
Yep, I have that ready. So thank you everybody for joining us for another Grease Teeth Thursday talking about analytical ferrography case studies. Today we have Ray Dalley of Trico and Rich Wurzbach of MRG Laboratories. Ray has been performing research, manufacturing, sales, and marketing with ferrography for the past 30 years. He gives lectures worldwide for the Electrical Power Research Institute, the Society of Automotive Engineers, the National Lubricating Grease Institute, the Joint Oil Analysis Program Conference, and Society for Maintenance and Reliability Professionals, as well as the Society of Tribologists and Lubrication Engineers. In addition, he's the vice chair for ASTM D2965 Condition Monitoring Group. He has published numerous technical papers and reports in the area of lubricants and wear particle analysis, and holds memberships in STLE, ASTM, AFE, American Society of Metals, and is an executive member of the SMRP. Rich Wurzbach is president of MRG Labs and has over 30 years of experience in the development of condition-based maintenance programs. He is certified by the International Council of Machinery Lubrication as a machine lubrication engineer. He has over 30 years of ferrography experience, part of which he was responsible for the design and development of the Peach Bottom Oil Analysis Laboratory at the Peach Bottom Nuclear Power Plant. He has helped to advance ASTM standards and is an active member of the ASTM In-Service Lubricant Group.
Great. Thank you, Richard. Okay. I'm going to kick this off today. I'm going to share a few case studies that we've had here at MRG Labs. And these are going to be around greases. And then I'm going to turn it over to Ray, and he has some case studies as well. I think most of his will be oil related, but I'm going to focus on grease as we get things started here today. And the first case study we have comes from a starch refinery. This was a feeder for that process, an inboard bearing. And we had a customer taking the sample in reaction to a noise that the bearing was making. And so there's a number of different options you have when you hear the noise and you want to respond to that. It can be ultrasound, it can be vibration analysis, but in grease lubricated bearings, sampling that grease and analyzing it becomes another level to better understand what's going on. So basic grease analysis was performed on this, which includes a number of tests. These are all consistent with ASTM D7918 for in-service grease analysis. And from this testing, we found high ferrous debris levels, an increase in consistency of the grease as compared to its new condition, so a thickening, if you will, of the grease, and high moisture levels. And so that prompted some advanced analysis, and part of that follow-on test slate included analytical ferrography. Analytical ferrography showed some large beta red oxides. You can see a photograph here of those. And so these will form from poor lubricating conditions, for example, if you have high moisture levels in the load zone, and that corresponded to the ppm levels that we were able to measure in the grease for the moisture that had gotten into that bearing housing. So what do we do about that? In this case, it was some grease flushing to try to clear out that accumulated moisture. Also inspecting the seals to see how the moisture is getting in the first place, and then identification of that ingression point and correcting that. And so you can see some of these large beta red oxides present in the sample, in the grease sample, after being extracted and analyzed by analytical ferrography. So the customer was able, in this case, to identify a specific lubrication issue and change regreasing activities. And that, is in comparison to, let's say, if only ultrasound was used, or perhaps vibration analysis. They would detect that the bearing was indeed damaged. There was some wear that had taken place, and it would change some of the frequencies and the ultrasound decibel levels that you'd see, but not necessarily pinpoint the source of that. And that's where grease analysis came in. It not only helps with this particular bearing, but also gives the customer information that can be used to improve bearing lubrication methods across the board for this particular component and others as well. And then there was some follow-up grease analysis after these measures were taken that confirmed improved lubrication. And that's what really we want to see, is that we want to get beyond this initial event and then have reassurance that it's not going to recur and that we've addressed the issues that led to it by improving lubrication. So knowing about the issue here allowed them to have a plan, know the severity of the damage, and extend the bearings operation until a planned outage was coming up. And then, of course, we can take some of the learnings here and improve lubrication practices plant-wide. Not everybody does that, but that's one of the biggest values, is to take this knowledge and then say, where else can it be applied? Where else do we have assets that are at risk because of that? We have another one here. We do some root cause failure analysis, and a failed bearing was submitted to us. The customer took, I guess maybe the customer held on to the bearing in this case, and then just sent us the sample from that failed bearing. And again, we did the initial grease analysis, found high ferrous levels. We're using a tool called the FerroQ, which is an inductive coil measurement for greases. It's specific geometry, works really well with the grease thief and that sampling methodology. We also saw increased grease consistency here, and we see that sometimes when you get an accumulation of debris. Grease is basically a thickened oil when it comes down to it, and solids will thicken that. And if you have wear solids or contaminant solids, they can cause a grease to get thicker as well, affecting its operation. Our analysis also showed contamination, both environmental contamination, things from the surrounding area getting into the grease and getting into the bearing, but also mixing of greases. So the wrong grease had been added to this bearing as well. So the ferrography showed us ferrous wear. You can see the particles lining up in those magnetic lines of force there. You've got some black oxides present, some small and fairly uniform black oxides. And then you have some heat tempered particles that shows high temperatures were experienced during this failure. Not a lot of them, but those tempered particles, and you can see the discoloration in the center photograph there, pretty severe. That's high temperatures, could come from loading of the surface, localized high temperatures. Then you got the black oxides, which are indicative of inadequate lubrication of the surfaces. It forms an oxide. And that's what we got there. So the customer is able to identify, again, a lubrication issue contributing to this particular failure, help them to enhance their greasing process or increase it. And when they looked at the frequency that was needed here, from the calculations that you can do, from the data we get from the grease, as well as the fact that this is a high contaminant environment, the frequency of greasing is high enough that they decided to install an auto luber, and then they can decrease the volume of grease that's being added, but increase its frequency. So more often they're kind of pushing out the bad grease, pushing out the contaminants, protecting that bearing. They did routine grease analysis, and that confirmed that this new setup gave them enhanced lubrication. And another thing, when you do that with an auto luber, you can actually optimize the frequency of lubrication using the grease analysis data by looking at the condition of the grease that's being purged out. And so the value then extends beyond just this one failure, this one bearing, to systemic improvements that can be made in grease lubricated assets across the organization. Got another one here from in this case, a paper mill. There's a high pressure feeder. And again, sample being taken after the bearing failed. We'd like the sample to be taken before the bearing fails, right? To find these sort of things, to look at these conditions and changing conditions ahead of time and take efforts to avoid the failure. But sometimes we're playing the catch-up game, and that's the case here. Grease analysis showed, again, high ferrous concentration in the grease, an increased consistency, and then specifically the contamination here being a combination of moisture levels, which in a paper mill is always a battle, right? You always got water, high levels of water that you're fighting as it tries to get into your machine, bearings and so forth. High moisture levels, high environmental contaminants, as well as, again, mixing of greases. And that just shows a lack of control in your lubrication process where, either a supplier is giving you a different grease than what you're adding to it, or you've got multiple technicians using different greases. And it does create a problem with compatibility. So ferrography here showed the ferrous wear that we saw, some red and black oxides, and then some sliding wear, some larger sliding wear particles as well. And so the sliding wear gets generated by excessive load or speed issues on a sliding surface where you lose that hydrodynamic or elastohydrodynamic film, and you get disparity contact. The black oxides, that's inadequate lubrication of those surfaces. So we had a combination there, again, ferrous sliding wear, the red and black oxides that you see there. And as a result, the customer is then able to identify this as being a lubrication issue. And mixing lubricants has a large negative impact on asset life. Understanding that that's an issue within a facility, maybe not just with this asset, but other assets as well, gives folks an opportunity to address that. In this case, the recommendation to use some color-coded or visual indicators to remind the users of the correct grease for the equipment. And there's some neat products out there for that, little silicone bands that can go around your grease zerk fittings, and you can put the same color band around the grease gun so that only that color designated grease gets inserted into that equipment, and that can really help when you're trying to make changes there. Usually you got to add a shape too, because not everybody has that color acuity, and we want all of our technicians to be able to follow these human factored improvements. But the routine grease analysis would find these issues, like when incorrect grease is added. And if it finds that early, because we're doing grease analysis routinely, we can see that prior to equipment damage, and it can be purged out. So, in this case, we had a failure, but it doesn't have to be a failure if we're getting in there to follow up with some more routine analysis and just take that effort to purge out the bad grease, purge out the contaminants, and extend that equipment life. Here's a wind turbine main bearing, and this is one area that we've seen a lot of usage of grease analysis. And again, we started here with our basic analysis test slate, and we saw some high copper levels. So we're looking not only at the ferrous concentration, which is important in a lot of applications, but it's good to know also when your metallurgy kind of dictates that you need to be looking at your elemental concentration as well. And more so in greases, we see that, you get almost a pure ferrous, metallurgy that you're dealing with. And so the ferrous debris to measurement is really covers a lot of bases. But knowing when your bearings have non-ferrous components as well, it says, hey, let's look at that. So from elemental spectroscopy, we had some high copper levels. We saw increased consistency again. And like I said, it shows up a lot when we have a high wear levels. And this is something that's different between oils and greases. Ray's going to talk more about some oil applications. And in oils, when you are generating wear, you tend to hit this equilibrium particle concentration where the particles are being produced, they settle out, they get filtered out, and they hit this certain level that may be going up over time. However, with greases, it's continuously accumulating. So the particles don't have anywhere to go. So you typically expect higher levels of wear, but knowing what those levels are and then what is considered excessive is important. And then as we get severe wear conditions, very quickly we get the accumulation of that particulate, that wear particulate, that impacts the grease consistency too. And not only is that something we measure, but it's also something that changes the way the grease moves within the bearing, how effective it is at relubricating. So all that's really important to see in the analysis. So we had that. We also had the contamination again here, moisture, environmental, and then mixing of different greases here. The ferrography, and you see the image here, what's really striking about this one is the change in color and then the position of those particles and the orientation of those particles. Instead of lining up in those magnetic lines of force, we see them dropping in between them. We see the major diameter or the major dimension of those particles not being aligned in that magnetic field. And that's a clear indication that they're non-ferrous in nature. So we got non-ferrous metals there. We've got red and black oxides and some sliding wear from this main bearing. Some more pictures here. We had to do a pretty, some dilutions here. You can see some very large non-ferrous copper alloy wear, also some rubbing wear there, quite a bit of rubbing wear there as well. And when you think about this being a ferrous bearing, where the rolling elements are ferrous, the raceways are ferrous, but the cage is copper alloy, you are having that rubbing contact to create that wear. So you're going to get both. You're going to get the ferrous wear and you're going to get the copper alloy. But obviously here, the copper alloy from the cage is producing the largest wear particles, the severe wear particles, and it really has our attention at first. So this customer is able to identify this wear issue. And it was, again, the lubrication condition causing the wear on the cage of that main bearing. And you've got the excessive quantities of particles actually are like self-feeding into the process, that they interfere with the effectiveness of lubricant. They become almost like a lapping compound that increases the generation rate of the rubbing wear, leads to the formation of the severe wear. Cage wear is in these large bearings is particularly concerned because it leads to a loss of structural integrity, and eventually you can have catastrophic bearing damage. So the elements start to skid. Sometimes if there's enough damage to the cage, the elements turn sideways, and we see that too. We see this huge sliding wear show up. Now, we didn't see that yet in this instance, but that's something that particular operator needs to think about. This is what happens, and then ultimately you get a clearance loss. And that clearance, as that opens up on those main bearings with all the forces from those large blades spinning around, can really lead to catastrophic consequences. So early detection could be a low-cost up-tower repair. And if you can't fix something up-tower, that means you're bringing in a crane. You're bringing in a mobile crane, you're setting that up, and you're going to be spending about $300,000 for every event. Now, not only is that an issue, you want to get early to that, but this also drives home the point of the value of regular and routine grease analysis, not just on the ones that you suspect a problem. Because if you're going to spend the money and the time to bring that crane out to set that up, you don't want to just fix that worst obvious bearing while it's there. If you can also leverage that to get a second or a third bearing that you've also found are compromised and close to needing that crane, you can save a lot of money. And so that's about, this is about alignment of maintenance tasks, maintenance planning activities. You can't plan for what you don't know is going to happen or is already happening. And a lot of times there's damage already happening in these wind farms, and all they're aware of is the thing that went out, the thing that went south. And unless we're testing the other ones, we don't know what we could align, what we could group together and more efficiently assess within a facility like this. I wanted to throw one more in here, which was a kind of a big recent one for us, where this is on helicopter grease analysis. And, before we started here, Ray and Richard and I were talking, and I mentioned about how Ray was my first mentor in analytical ferrography. And I remember that was one of the things that he was telling me about, was helicopter swash plate greases was one of the things, 30 years ago that he was doing for some folks. I don't know whether it was Canadian military or who it was at that time, but he brought that up and shared that with me. More recently, Boeing reached out to us. They were asked to optimize maintenance for the Chinook helicopters. And these are the tandem rotor helicopters that are deployed around the world. And in this case, the Canadian, the Dutch, the UK, and the US military went to Boeing and said, help us address the maintenance activities here. And this is basing this off of, this is an aircraft that was designed in the late 1950s, went into production in the early 60s. And as I became part of this project, some of the maintenance manuals that we were reviewing were dated back to 1962. So you've got maintenance practices that are a bit older than me anyway. And so instead, it's like, well, let's base it off data. Let's base it off of what's actually happening in the field to these assets. So as part of this project, we created grease sampling tools for the swash plates, for the drive splines, for the hanger bearings, and for the landing gear, all of this following the ASTM standard D7718 for in-service grease sampling. We performed over 9,000 grease analyses, and it was on for all these different fleets, from aircraft from these different fleets in different operating environments. Sometimes it was in the far north, the Arctic area that they were being deployed to. Others were in Mali. In fact, the helicopter that you see at the lower left on this slide, I thought this was real interesting. I was doing some research and I found a YouTube video, and this was for a UN humanitarian mission in Mali. It's basically a flying hospital in this case. But I noticed the tail number on this, and it was a tail number that matched up to samples that we were receiving in our laboratory. So we had a direct connection that we knew that we were directly responsible for evaluating and testing the grease from this particular helicopter. And knowing their mission was kind of neat as well, knowing the good work that the Canadian Air Force was doing with this particular asset. But this is what we did here. And then again, maintenance intervals in place since 1962. The only modifications in that time had been in response to issues, perhaps a previous crash or a near miss type thing. And what would they do? They'd say, well, grease more often. So over time, without data, it was just, well, whatever it was, let's just grease more often. So there was this opportunity to look at what is the condition of the grease. And by doing so and using those over 9,000 grease analyses that were done, we were able to reduce the number of lubrication tasks per 1,000 flight hours from 98 down to 56. So almost cutting the amount of work in half. And then the amount of time that they spend in the field, reducing from 20 service interruptions to just 10 every 1,000 flight hours. So basically, the aircraft is spending twice as much time in the field. And more recently, here in the States, we saw what happened in our mission in Afghanistan. And as we were trying to evacuate out, time was of the essence. And when you think about an important asset like this, that where time is critical, if you can spend more time in the field without having to take it back for depot maintenance, it's more effective, it's more productive. But the operators themselves estimated there's an $80 million maintenance savings per year across this fleet as a result of grease analysis. And part of that did indeed include our evaluation of the failure modes and the wear modes, I should say the wear modes, using analytical ferrography. So I just wanted to finish up with that and give you some of these case studies in this background and just how valuable analytical ferrography can be in helping with grease analysis. So I want to hand that over to Ray and have him share his with us now.
Good job, Rich. That's exciting to see how it has bridged over from what we used to do back in the late 70s, early 80s with the U.S. Army, the Canadian Armed Forces, and then having you checking on these Chinooks, CH-47s. That swash plate situation is a phenomenon where the dust curls up and goes right back into the hub Well, if you'll notice helicopter designs today, they have what they call like a frisbee on top of the hub, which
Right.
prevents that type of situation from occurring. So since then, they don't have it as much as they used to, but at least they know how what was going on and to prevent that particular failure from occurring again.
Yeah,
So
absolutely. And if I can comment on Ray, that frisbee, we had to move that out of the way to get our grease sample, right? But
exactly.
but we were also, in those analyses, we had 7 parameters we were looking at. One was the silicon levels as an indication of sand and dust getting in there. And there was maybe one situation where, and it wasn't in the swash plates, where dust was potentially a concern, where you got to purge the grease out for that. But most of it was oxidation, that the grease was coming to the end of its life, and we
Gotcha.
were changing it out based off of that. So thanks for giving us that that feedback there. Yeah,
No
that's great.
problem. No problem. I have a few case histories myself. As Rich indicated, they're oil related, and they're not going to spend too much time. But I have one at the end, which I thought it was pretty exciting share with everybody else. The next one that I have here is one of a conveyor system at basically a coal fired plant down in Texas area, South Texas. And you'll see the gearbox on to the left, and you'll see the plant in the middle, and you'll see the related particles to the right. Basically, by seeing that, they were able to at least do a maintenance review and basically prevented a failure from occurring where the coal basically could convey it all the way up to a certain height and then get spread into the feeder and so forth. So it prevented them from having a shutdown over a period of time, and then that saved them a good amount of money of almost 60 to 70 grand, basically. The next one is a case study where it's a bowl mill, and what I did was they were allowed us to took photos of the mill after when the maintenance occurred. Obviously, they had to shut it down, take a look at things, see what uh, basically what improper things were going on with the gears themselves. And by virtue of being able to not have an emergency shutdown, they were able to save at least 1.2 million dollars. You can see the gears themselves right here in the left bottom and left, and then the weird related particles onto the right itself. I have on the next photo, I have or next slide, I have basically the animation of the ball mill, the technical drawings of it on the right side, and then the related particles in the middle of there. And this customer was very elated to be able to use the technology of ferrography for long periods of time. To this day, they've been a customer for us for almost 30 something years. So we have good relationships with this customer, and they believe in the technology. And by virtue of being able to pinpoint exactly what's going on, it makes that much easier and feasible to, basically point the maintenance crew to the right areas of what's going on. And in this market today, no one wants to spend time searching for where the problems are. They just want to be able to know exactly where it is to fix it, because time is of the essence in terms of the maintenance staff and what they do. So I just wanted to share that particular one with you. The next one is a very interesting situation where I think I gave a talk some years ago to Electric Power Research Institute, and I shared with them regarding this particular situation. This is just the what we do with the lubricant. We tested it at 40 degrees. We ran an FTIR. We ran a TAN, Carl Fisher spectrometric by ICP, induced coupled plasma spectrometer. We ran a particle count. We ran a direct reading trend, and we also ran ferrography with photomicrographs. We did this on a monthly schedule. They were able to send the samples to us, and this is at NASA Goddard facility. They have one of the largest, what I call clean room in North America. And what happens is we were involved with them from a viewpoint of looking at this particular application. But what they do is, if you remember the Hubble's telescope, they were having problems, not in the beginning, but they found out about problems they had with regard to the polishing of the mirror. And what happens, they had to go up and make these fixes in space. So what they're doing now is they're making sure that that's not the case here, because this is the Webb space station. I mean, not space, telescope. And this telescope is going beyond the moon to go and look and take photographs of what's going on. So what happened is that their clean room had some issues with regards to a combination of what I call electric motor drive, coupled with a coupling gearbox and a compressor. Obviously, the compressor is used to bring the torque down into the clean room environment to make it super ultra clean. So, and in having that environment allows them to polish the mirrors for the Webb telescope. It's named after a gentleman named James Webb, who was very influential in the Apollo program. He's an administrator in that particular area. So what you see here is a compressor, a gearbox, a coupler, and an electric motor. And what happened is the electric motor was one having all different difficulties, but it was a oil that was all over the place that we were able to getting sampling from and so forth. So in doing so, you can see it's a York double stage compressor. Funny enough, the town of York is where Rich is. So that's what helped me pick out one of these presentations too. So I figured I'd give him a little kudos on that part too. So, but it was a double stage compressor. And what happened is, here's the gearbox. The gearbox had no problem, running real well, doing everything. But when you have these lubricants, you have to do research and find out exactly where you're sampling, where all the different things come into play. Is it a grease situation like Rich would mention? Is it from the compressor? Is it from the electric motor? All these things come into play in terms of your your systems that you're monitoring, because it's not just one item that you're going to be looking at. But in this particular case, we were able to focus in on where the problem was, and that was from the area of the electric motor. It's a large, 4,000 horsepower motor, that type of thing. As you can see, in comparison to the Hubble, this is just a quickie overview of what the difference between the Hubble and the Webb space telescope. As you can see, the cost for the Hubble was $2.5 billion. The cost for the Webb space telescope is $8 billion, and that's numbers back in the 2020, 2019. Okay, this aircraft was supposed to be this telescope was supposed to be up in space by this time, but there's delays, there's inspections, there's all kinds of different things that they don't want to put up something that they got to have to go and fix, because guess what? It's not a quick trip to the orbiting of the Earth. It's a trip to the moon. This is where this particular Webb space telescope is going. So that's why there's so much contingency, so much different things going on to make sure everything is spot on perfect in regards to what's going on. So what happens here is the size of this particular unit is almost for the Hubble is 43 feet long. For the Webb space, it's almost 70 feet long, and it's going to be almost the size of a Boeing Jet 737, basically. Okay, so in this case study, you can see this is where the Hubble telescope is, and guess what? The Webb telescope is going to be beyond the moon and encircling around the orbit of the Earth, basically. And you can see this is the mirror of the Hubble. These are the mirrors of the Webb space station, space telescope. So you can see it's a dramatic difference of what's going on in that direction. So what happened here is whatever we were doing was basically messing up the time frame of how fast they need to get this going. The good thing is we were planning what's going on in regards to monitoring the situation. So the first report showed them that they had a critical back in July of 2014. They were not planning on this. They're not used to monitoring what's going on. They had normals all the way across before, and all of a sudden they had a marginal, and then all of a sudden a critical occurred, both in the lubrication and the equipment condition basically was starting to have effects on the problem. So what we do, we basically monitor and say resample, because you don't want to err on this. You want to err on the side of caution, not on the side of, okay, we got a problem, you got to shut it down, and you don't want to mess up with production or anything like that right away. So what we did was we started trending the WPC with the DR, and we also started trending with the wear metals with the ICP. Both were indicating that the wear rate was going up. Rich had mentioned that we have an equilibrium situation with regards to taking analysis. So every time we have a sample, it basically gets to a normal level, and then the larger particles start to trend upwards. And this is what you're monitoring here, is the larger particles that's going up in this direction. Whereas also on the spectral, we're also trending the smaller particles that are going up too. So not only are we getting large, but we're also getting small too, and what's going on in the situation. So we got back to the customer, and we saw not just the trending of the wear debris, but we also saw large amounts of copper alloy particles increasing. They're very aggressive, and this is a close-up picture at 500x magnification. The picture, the photomicrograph that Rich showed before, showed particles in between the strings of ferrous debris. Well, these things were so large that you didn't have to worry about being in between the strings of the ferrous debris. They were large enough to cause all kinds of issues and so forth. So we told them that they need to take a quick look at what's going on, and they couldn't afford the time frame to do so. So literally what they did was they kept changing oil every few months just to limp this thing along, because they wanted to keep the clean room clean environment, and we're praying and hoping nothing shuts them down. They had backups after backups that's in play and so forth, but they still need to use the machine for bringing the torr levels down to a certain area. So we saw 3 criticals in 2-year span with oil changes occurring. Now, what we did then is, once we saw that last critical with these large, humongous sized particles, we said, guys, you're going to have to make a move. Something's going on where the particle count is getting really elevated. The wear metals, the contaminants, everything is starting to climb up. So we provided a report. We saw the particle images. We said, come on, guys, this thing is laden with all kinds of copper alloy. Okay. If you keep going in this way, you're going to have a catastrophic failure, and you're not going to want that. And that could mess up the situation with debris and contaminants flying possibly back into the clean room environment. Yes, Rich, you were looking. Oh, thought you were going to ask a question. So you could see there was different types of photo: large copper alloy, bearing wear particles. The thing that I noticed when Rich was showing his photomicrographs of the beta red oxide, there's a phenomenon that you have to make sure of. Sometimes these red oxides may look like metal, and you must turn off the top light and turn on the bottom light to actually see the light go through the red oxides to actually indicate that it's red oxide in that direction. These are different tidbits that you have to know in terms of monitoring the ferrography, the photos, the particles in ferrography, in analytical ferrography. So that's part of what we teach sometimes in our classroom, some of the tidbits to notice what's going on. So, but these photomicrographs, these are at 200x. This one's at 500x. So you got to know what the magnifications are, what the dilution factors might come into play, and so forth. And this is, mind you, is oil related. And you can see they're not lined up in strings of ferrous debris. They're all copper alloy, and that's not a good sign, if you know what I mean. So when we saw that, we said, listen, guys, we got to start figuring out what's going on. So they stopped, they took apart, and they basically looked at the electric motor, and what they found in the electric motor is basically, let me go back. What they found is the cost for doing this was pretty not what they wanted to spend, but it beats having to spend $8 billion on a lost telescope, if you know what I mean. So that's a little nothing compared to $8 billion, $80,000. So they scheduled the maintenance, they got it repaired, and then what happened is we asked the repair people, with the NASA's permission, obviously, can you at least give us some photos of what you saw, what transpired, what kind of parts are broken or anything like that, if there was any, or and typically most customers don't reply in that fashion because they like to keep that buried and not say that any one of their machines are running imperfectly or anything like that. But the vendor and the government said not a problem. This is a good learning lesson tool, so we're going to pass it on to you, and that's what we saw here. So the awareness of the drive motor issue was labeled on the watch list. This motor was like 31 years old, but it was scheduled for repair. The repair happened quicker than they anticipated, and so it wasn't in the budgeted for the upcoming year. But after the latest critical, they said, let's get this all squared away, and we would not lose any downtime whatsoever. So our investigation, along with theirs, indicated that they needed to filter their oil coming into the facility. They were getting deliveries of bad, or I would say, nasty oil, or oil that was not up to cleanliness levels that should be put into the motor or into the compressors or into anything like that. So we literally just provided them a very easy, simple process of just cleaning their oils that's just sitting around using a drum pump filter, using different filtering situations and so forth. And it made it that much more appetizing for them to be able to absorb that instead of an $80,000 course or anything like cost like that. And it wind up them basically having a great implementation of having them do the things they need to do for creating the Hubble telescope to be taking off, hopefully coming up this December. So the next few slides are just little indicators of what the parts look like after they did their inspections from a maintenance viewpoint. As you can see some really gouging metal from their bearing area, and you can see it's obviously copper alloy from these bearings here. You can see that this one is a drive end. That's what that DE stands for, where they can see more damage that's going on with the bearings themselves and so forth. So again, copper alloy material, just showing what's going on, and you can see all these different catastrophic type situations that could occur. You can see how it almost just slides on the bearing right there, and gouging what's going on. And that's where you see a lot of what I call severe sliding wear on the copper particles and so forth. We were measuring 70 to 90 microns in size over a period of time. So, they basically cut it too close, in my opinion, for condition monitoring. This is basically repair of what's going on, and it's not what I call predictive maintenance, if any way. It's completely opposite of that, if you know what I mean. It's almost to the term of failure analysis, which Rich was talking about earlier, but the motor was still working in regards. Here's another copper alloy material, basically shedding away into the lubricant itself. So with that's I know we have plenty of time, but I was hoping that any questions may come up or anything like that. But I just want to first thank. Well, let me show you. Here's what the bearing should look like. That should be replacing it, and then the next photo shows how the telescope fits into what they call an Atlas II rocket, using Delta engines, and going to be hopefully coming out in October, November, December timeframe. And I hope this will be a success, but it's going to be tough for anybody to repair anything, considering they're going to have to take 2 weeks or so to get to the moon to basically do any repairs. So, and catching it in a certain orbit that's conducive for flight and what's going on. So when I saw this, I enjoyed the fact that I was able to be part of this in terms of seeing this take off soon. And when it does and be successfully deployed, I'd be proud to say I was involved with the Webb telescope and hopefully working properly and giving us the images we're looking for in regards to deep space activity. So that's my case histories, Richard. And I want to just say before anything else, thanks to the people behind the scenes in making sure this webinar goes seamlessly, because there's a lot of activity in terms of production and trying to put something like this on, both on whatever you got it on Netflix or YouTube or whatever you guys got going back there. And I just want to thank everybody that's in the audience for at least attending and then being able to at least look at this, because it will be used on tape or on computers or whatever at any time. And I appreciate getting the invite to be able to basically participate in any area of ferrography. So I just want to say thank you to both MRG and their staff for getting this done in a very seamless manner. So.
Well, great. Thank you, Ray. It's great to get to talk to you when we can and to have your expertise. There's been very few people who have been continuously involved in a technology like analytical ferrography like you have for many years. I won't pin you down to exactly how many years that is.
I got to upgrade that resume. That says 30, so that's being kind.
Well, yeah, you were already the expert when you taught me, and I got 30 years. So yeah, sounds like it needs an update. We got to thank Richard Janoski, because he really did a lot of the work to set this up for us today and to kind of make sure we're pointed in the right direction, which is great. Just a question for you with that. I mean, obviously you're focusing on helping the folks at NASA with your technical input, but it sounds like you learned a lot about that mission at the same time, which is really cool. So I'm assuming that's an unmanned mission, and then it has to unfold and assemble itself once it's to its place in space. Is that how it works?
Your assumption is absolutely correct. Yes, It is an unmanned mission, and that's why they're going over every little area of specifics for the application itself, because the unmanned aspect of things is almost like by doing the Mars mission with their that little cart that runs around. That's literally the same signaling process they'll be using in regards to the telescope, but it's closer, so they're able to get feedback information much quicker than waiting for what's going on with Mars. So,
right,
in terms of a signal.
Yeah, there's some great stuff there. I remember I was at a conference a few years back, and the guy who was in charge of the Mars rover program was there, and he talked about their lubrication failure, where one of the Mars rover wheels ended up locking up, and they ended up dragging it around the surface of Mars for a while. But like plowing up soil and things, like farming on Mars. But no, your point is really important, because if we're using machinery to do these assemblies, right? We're using machinery to get these vehicles together, to get them ready and so forth. And if they're not quite right, that can have an impact, not only on schedules, but then on the quality that's out there, the dimensions, how they're made and so forth. So it's really neat to see that. Hey, if we could go backwards a little bit, I wanted to point out something in your presentation. And maybe I'll see if I can't take us back where I want us to go here. When you were talking about this York compressor, and thanks for the York shout out there. You mentioned too the flexible coupler. And I just wanted to mention that and you shared with us oil analysis from the motor side. That was what you were focusing on there. But obviously then there's the chiller. And it has lubrication, and that's a very complex lubrication system there with the chiller fluid and the oil, and they get together and things like that. But on that coupler, that really caught my attention. I was talking to Richard before we started here, because soon after you trained me and set me up, and we built that laboratory, and you went back to Ohio. I was asked to investigate a problem with Amerigear flexible couplers, which are grease lubricated. Right. And in my plant, they were feed water pump couplers. So from a large steam turbine to a feed water pump was coupled with these units, and we were having issues. And the interesting thing was that the mechanics, when they would look at that, would identify that the couplings were rusting out, because they saw a reddish dust instead of the grease that they know that they put in when they set this up. They said, well, the grease is gone and now they're rusting. So that gave me an opportunity to look at this further, to take the residue and find that in fact the grease is still there. I found the evidence of the grease, but the particulate was a red and black oxide, very uniform. and clearly a sign of fretting.
Yes.
And so once
Okay.
we were able to determine that fretting wear mechanism, that allowed us to go back and evaluate the operating parameters of that coupling. And what we found is that not only was it pretty significantly misaligned, but more so than that, in operation, it had a variability in rotational speed. So the coupling would load up and unload, load up and unload. So it would squeeze the grease out over time, and then you start getting metal to metal contact back and forth, that reciprocating metal contact. And that's what produces fretting wear. That is a fretting mechanism. But through grease analysis, and this could have been weeks or months after you turned me loose, as a freshly minted ferrographer, that I was able to use this technology and pinpoint the nature of that. And what we found in that case was that those parameters were a function of the way the plant was designed. We couldn't change it. We couldn't, believe it or not, we couldn't even change the misalignment because of the piping strain and so forth. So we actually completely left that behind, went to a new style coupler. Now that's 28 years ago or whatever it was. They're still operating. So we had 4 failures in rapid succession, and we would have been continually changing those assets out, except that we were able to use grease analysis and specifically analytical ferrography to understand the failure mode and correct for the failure mode. And that's what I think, if you look at what you talked about here today, what I talked about earlier, is the takeaway. And when, and obviously we don't do and customers shouldn't be doing analytical ferrography on every sample that they take. That you need to be screening for that. You need to know when you've got abnormal wear, and it makes sense to dig further and to get this information. But I believe that analytical ferrography is one of the most powerful tools we have to understand what are the true underlying causes of those failure mechanisms, so that we can change things in a way that they don't come back and get us again.
I hear you. That's a very good point that you made with the coupler. It's in simple terms for other people out there. It's almost like a bending and breaking of a paper clip, back and forth, and that's what you get in terms of regard to fretting and fatigue failure, basically going on with the coupler itself. That was very good on you. I'm glad I was able to take care of my ace student in terms of him learning what's going on and how to basically take care of that particular situation with grease analysis. So
well, it's why it's great for me to still be able to work with you today and to look at things together like we have today, and share some of this with other folks. But what I'd like to I didn't see any Richard. I didn't see any questions.
I got one question that got sent over to me, and it was just asking about, we had talked about certain specific particles that we had seen earlier, and it was just asking about what kind of particles could be classified when you're running analytical ferrography. And I can kind of help with this because I was preparing ahead of time. But when we're looking at different particles in analytical ferrography, we could come across, obviously we mentioned ferrous particles, so they could be severe wear, it could be abrasive wear, it shows signs of fatiguing. We can then also have our non-ferrous wear, so that would be like copper alloys or other wear metals that might be in the system that are capable of creating other hard particles that are not ferrous. We also might get different iron oxides. We talked about those. Those are our black oxides and our red oxides. The nice thing is when we see those, they form from different mechanisms. And even like Ray mentioned too, with the beta red oxides, our alpha and beta red oxides help us indicate the way they formed, because they do not form the same way. So we would know more of, is this, it helps us determine the root cause of why that particle is showing it. Ray's got right there the wear particle atlas.
You can get an atlas. You can get a particle, a poster that I provide just to make it easier for anybody that's interested. You can get that information through Rich. I'll have him have a supply of it so that he can easily give it to his customers, whoever might be interested in having that wear particle poster. That poster basically is designed almost 30-something years ago when Rich first joined, and people still utilize it today. Obviously, we're trying to put together what I call a digital poster in terms of having a lot more content that's in play. So, and that should be coming out within the next 6 months to a year, somewhere around there. So just to let people know ahead of time. It's a little, I guess a little, tease in the video business, I guess, in that direction. Okay.
Right.
So,
Yeah, Ray. I was going to bring that up as Richard was starting to go through the list. I was going to say, hey, Ray's got some posters for you. And we'd be happy to respond to people who are connected to us and make sure they get into their hands. But I did throw your email up into the conversation box here
that'd be
that people
fine.
could
can
reach
easily-
out to you directly. And
Yep.
and you played a big role in the early days of identifying what those different particles were with a group of people who I think they're all retired except you now.
Yeah, you're right. Yeah,
But we're
correct.
we're fortunate to still have you as a mentor to us all who's doing analytical ferrography, which is great. And I really thank you for this. And now my job is going to be to try to find another excuse to invite you back again, Ray, and to do this once again. But I'd like to thank you for your time today. Richard, was that the only question that you had, or was there anything else there?
I didn't see anything else come through. Nope.
Okay. Richard, so can you talk a little bit about what we have coming up next for Grease Thief Thursdays?
Yes, I can. So next month on the third Thursday, we are going to be discussing our new filter kit. So that's similar to the RCFA kit we talked about before, and we'll discuss the benefits of doing filter analysis and having that kit on hand for if you do have a filter issue. And then we will be taking a break for December, and then we'll be back starting fresh in January for the new year.
And what's that date in November we have scheduled for that?
The November date would be November 18th. It'll be November 18th at 1 p.m. for the discussing the new filter kit.
Yeah, that's pretty exciting because we've noticed that sometimes folks send on filters, but it's a bit of a mess. The oil's leaking out everywhere. The filter gets smashed. Some of the data is lost. And so we're going to talk about a way to capture that at the site as you're disassembling your filters and to put them into a container, an apparatus, into a kit that we've developed that helps you gather the oil condition as well as retain the condition of the filters. Because recently we've been finding that the shape, the damage to the filter tells a lot of the story about what led to it, what happened, and what you need to do differently to protect your equipment in the future. So we're going to share that, and I'm looking forward to that. That finishes us up for today. Thank you very much. And again, we'll have this available to replay later on YouTube, and I'll share that link to those who joined us. Thank you very much. Have a good day.
You too. Take care. Bye-bye.
All right. Bye now.